Hi everyone, welcome back to Modern Portfolio Theory and Investment Analysis. In the last couple of chapters, we talked about how the efficient frontier looks like for risky assets. And in this chapter, we are going to talk about some techniques to calculate the efficient frontier. Okay, so this is a math heavy chapter. So it's kind of, a lot of math is there. But this is the only chapter where a lot of math is there. And in fact, most of the calculations that we are going to see today, it's basically done by solvers. We are only going to learn some methods. So the calculations are actually done by computer softwares and mostly like the solvers, optimization solvers. But I think it is still like very much necessary for you to understand what's going on behind the scenes so that you can appreciate the complexity of it, and you can understand the purpose of the upcoming chapters, next chapters, where we try to simplify things even more. Okay, so in this chapter we are not going to simplify anything at all. So let's see how the calculation of efficient frontier, efficient portfolios basically looks like. Okay, so let's start with recall, right? So if if we have two securities, right, with return R1 and R2, and if we invest X1 fraction in the first security and X2 fraction of our budget in the second security, then this is how we can calculate the return of the portfolio, right? And this basically extends for more than two securities as well, right? So if you have more than two securities, then you just put X3, R3, and so on and so forth, right? And obviously the sum of x1 plus x2, or if you have more than that, then all of those sum of x should be equal to 1, right? And how we calculate the variance, it's also kind of just a recall that this is how we calculate variance for a portfolio where the variance of individual securities are given, which is sigma 1 square and sigma 2 square, as well as the covariance, which is sigma 1 2, is given for every pair of securities, right? So this is for just two securities. If you have more than two, then for example, with the third one, it will be a few terms added with x3 square sigma 3 square plus 2 times x1 x3 sigma 1 3 plus 2 times x2 x3 sigma 2 3. Okay, and as I said, the x1 plus x2 should be equal to 1. And sometimes you are not really given covariance, but instead you are given this correlation coefficient, which is rho 1 2. So using that, you can actually, if that and the standard deviations, which is sigma 1 and sigma 2 are given, then you can calculate the covariance, which is sigma 1 2. Okay, so in this chapter, we are going to calculate efficient frontier, right? So the learn some methods to calculate the efficient frontier, and we are going to go backwards, right? So this is something that we learned last in the previous chapter, which is everything is allowed. Short selling is allowed, lending and borrowing and everything is basically allowed. And so in that case, how do we calculate the efficient frontier? So we recall that if we plot the graph between return and risk, which is sigma, it looks something like this, right? And so with there is also a line going, which is this blue line is the efficient frontier for our case, right? So this is basically how the risk and returns vary for different combination of securities in our portfolio, and this is what is called the risk-free return rate, right? So something that we can borrow from bank, or we can give it to bank, we put it in bank and we get the return RF, right? So single risk-free return, let's say, right? So this thing we learned at the last, and we are going to start backwards because this is actually the simplest case. Okay, so in this case, all we have to do is just calculate this line, right? So for calculating this line, the equation of this line, we already have one point, which is RF over here, right? So which is on x-axis it's 0, y-axis it's RF. And if we know just one more point on this line, then we can basically very easily calculate the equation of this line. And equation of this line is the entire efficient frontier, right? So what we are interested in is calculating this point, right? So where it intersects this, combination of our securities, right? So this point is a special point, and it's basically like this curve, right? This line is a tangent to this curve, right? So in other words, we can say that if we have an angle of this line, slope of this line, which is theta, right? So this theta is maximized, the slope is maximized, right? So the lower slope basically will mean going from here to here, like so some line, something like that. So let me actually draw it. So something like that, right? So this is another line, but for this particular portfolio, which is not really the optimal one. And so we are interested in particularly this one, and so we are interested in looking at the line which is passing through this, and this angle, right? So this is the theta angle which is maximized, right? So for this one, the angle, that same angle is very less. For this one, it is the most, right? So if we try to increase that angle even further, if we try to go even further in this direction, we will hit infeasible space where we don't really have anything, right? So this is the maximum we can go in this direction, and this is where we're interested in going, because this is where we get higher returns for lower risk. Okay, so what is the slope? The slope is basically, you can calculate it with this equation, right? So it is this is the return of the point where we are touching that curve, right? Which let's call it RP bar, portfolio return, let's say, and we also have the risk-free return, and this is basically the y values in our line. We subtract the y value, we calculate the difference in the y values, and the difference in the x values is the actual risk for that portfolio that we are taking, the risk for that particular point in that curve, right? So this is what we are trying to maximize. Okay, and the only constraint that we have is that sum of all xi's should be equal to 1, and recall that these xi's are our real variables, right? So if we know the values of x, then we know the point, right? So then we know like where exactly we are in that curve, and so then we know what is the value of RP, then what is the value of sigma p, right? So in fact, RP and sigma p are defined in terms of this x, right? So how depends, they basically depend on how much we are investing in which security, right? So let's actually try to substitute this equation directly inside this one, right? So the coefficient of RF is 1, and this entire sum is equal to 1. So let's, if we put it or x sum of xi over here, and then we actually expand the formula of RP bar, which is sum of xi ri, right? So it, and then we take the xi common, which is xi times now it will be ri minus rf, right? So initially RF was outside this summation, but we can its coefficient is 1, and if we replace that coefficient by sum of xi, then we can take the xi common outside of this equation, and then it will look something like this. Okay, and of course, like the standard deviation formula, it's I've just put it here as it is, right? So this is a simplified formulation, right, where I goes from 1 to n, j goes from 1 to n, and we are multiplying xi xj times sigma ij, right? So when I is equal to j, this will become xi square sigma I square, which were like the square terms in our, like the first set of square terms in our summation, and the other terms are like 2 times xi xj sigma ij, right? So the 2 is basically hidden because once it will be written for ij, and second time it will be calculated for ji. Okay, so this is a very simplified notation of having that, right? So we're trying to maximize this one. Okay, so this theta. So how exactly are we going to do that? So the easiest way to do this kind of maximization is take the derivative, right? So we are trying to optimize for our x variables, right? So take the derivative of this theta expression with respect to xi. So I'm not really going to take you through the steps. I'm just going to show you what it looks like when you take the derivative, right? So it's slightly involved, but if you are like a proper math student, then you should be able to calculate the derivative, right? So if you take the derivative d theta by dxi, then it will look something like this, right? So the lambdas are constants. We have the first set of terms will look like this: minus lambda x1 sigma 1i minus lambda x2 sigma 2i, and so we basically take the minus outside, and this is basically like the sum of these terms. For xi, the ith variable xi, it will look something like lambda xi times sigma I square, and for the other ones it will be lambda x whatever times sigma something I, right? So that's how the first set of terms look like. The second is ri bar, and the third is minus rf, right? So there are let's say we have n securities, then there are basically n such equations, right? And all we have to do is that make sure that these derivatives are equal to 0, right? So at the maximum point in our curve, all of these derivatives are equal to 0, first order derivatives, they're equal to 0. And so if you do that for each of them, right? So there are n equations. So d theta by dx1, d theta by dx2, up to d theta by dxn. And if we do it for all of them, and then we get system of n equations, right? So all of this basically looks something like this, right? So if you equate this to 0, then it is the Ri minus Rf, and then all of these terms will go on the other side of the equation. And let's say for now, I'm going to say that lambda x1, I'm going to represent it with z, right? So previously x are our variable, but now our variables are z, just to simplify things, right? So lambda, like having the lambdas are unnecessary burden, so we are just going to simplify things by putting lambda x equal to z. Okay, so there are again like n equations, one for each I, and there are n unknowns, z1 to zn. And so if we basically solve that, then n equations and unknowns, we can solve it. Like all of them are linear equations, and if you use basically simple methods like Gaussian elimination or something like that, then we can actually solve it. And we know the values of all z's, right? So once we know all the values of z, then we can calculate the values of x by simply doing this, right? So xk will be equal to zk divided by sum of all zi, right? So if we do that, then we get our proper answers for our x values, which is what we wanted. We found the point which maximizes that theta, and once we have that point, we can actually calculate the entire equation of the line. Okay, so that's the procedure. I know it's a bit complicated, but if you manage to understand it, then it is like the easiest thing to do. Okay, so all you have to, let's rewind what are the steps to calculate this entire efficient frontier, right? So first we start with all the returns, like collect all of this, like all of these are our inputs. So all the returns for each and every security, including the risk-free return. Then we need to know all the variances or the standard deviations, and we need to also know the covariances, right? So sometimes the covariances are not given, sometimes they are given in the form of correlation coefficients, right? So these are all our inputs, and of course, like the risk-free rate of return is also our input. And then we are going to solve the system of linear equations for z using Gaussian elimination. So, and then we calculate the values of x by normalizing the z values, right? So recall that the system of linear equations that we get are of this form, right? So we know Ri, we know Rf, we know all of these covariances, right? And so we know all of these equations as it is given our inputs, right? So we actually don't have to take the derivatives and all those things. So those are like intermediate steps that we have already completed, right? So z's are our unknowns that we are trying to find the values for, and once we have this n equations, solve for z. Once we have those z value, then we calculate the x values by normalizing this z value like this, right? And so that's how we calculate our efficient frontier. Okay, so just to make sure that you understand the procedure, let's actually go through this example. Actually, I'm not going to solve this example. This is like your exercise, and you are going to solve this, and I'm in the next slide, I'm going to give you the answer. So if you want to solve this, and then pause the video somewhere, and then I'll reveal the answer, right? So the returns are given for, there are 3 securities, right? So the returns for all those securities are given. The standard deviations are also given, and the correlation coefficients for each pair is given, like so 1 2 1 3 and 2 3 are given. So all the details are given, and the risk-free return rate is given, and your job is to calculate the efficient frontier, that portfolio of these x values, right? So that's the challenge. Pause the video now, and I'm going to reveal the answer in the next slide, which is here. So if you calculate the equations that I just described, so those equations look something like that. This is the first intermediate step, right? So it is 36 z1 9 z2 18 z3 equal to 9, and these are the 3 equations, and if you solve them using Gaussian elimination, then you get this answers for the z values. So if you don't know the Gaussian elimination, actually even Excel can solve that. So you might need to search that in Google somewhere, that search that how to solve a system of linear equation using Excel, and then you'll find some very good tutorials how to do that, right? So just plug in these numbers and then you'll find these values for your Z variables. And once you have these values for your Z variables, you just sum them up, which is 18 by 63, and then divide 18 by 63 by for all of them, right? So x1 will, you will get 14 by 18, x2 you'll get 1 by 18, and x3 you'll get 3 by 18, right? So this is the final answer. Okay, so previously we talked about short sales allowed and riskless borrowing and lending allowed, and now we are going to talk about short sales allowed but riskless borrowing and lending is not allowed, right? So that's basically, this is the risk-free return rate which we imagined, like which we used for calculating this equation of this line, right? So now we assume that this line is gone, like this, right? So that line is no longer present. So now our efficient frontier is not that line, but instead this curve which extend to infinity, but from here to infinity, right? So here is basically where the lowest sigma is, where the lowest risk is, all the way to infinity, right? So we have a bunch of securities, and this is the efficient frontier. Okay, so how do we calculate this, right? So if we have this kind of a line, then it is easier to calculate one point in this efficient frontier. But if we don't have that line, then we don't know anything about it. But on the other hand, if we know, let's say, somehow 2 points on this efficient frontier, then as we learned from the last chapter, it is easier to calculate the rest of the efficient frontier, right? So any combination of those 2 points on this efficient frontier is also going to lie on that efficient frontier. And also basically all we need to do is somehow find out any 2 point on this curve. Okay, so how we are going to do that is very simple. We are going to imagine that there exists some RF, right? So we don't have any risk-free return rate, but let's say if 4% risk-free return rate is, let's assume there is a 4% risk-free return rate, or something like that, RF is existing, then we have this line, and then we can maximize the theta, and then we can calculate this particular point where it is touching this curve, right? So 1 point on this efficient frontier is, we can easily calculate it, right? So that's 1 point. And for the second point, what we are going to do is we are going to imagine a different RF is there, right? So instead of here, let's say our RF is somewhere over here, and so it will touch this curve somewhere over here, right? So one RF which is over here, other RF over here, and so one of them will touch here and other one will touch somewhere over here, and then those are our 2 points that we needed to know, right? So once we have those 2 points, then we can basically calculate the rest of the efficient frontier by taking combination of those 2 points. Okay, so let's revisit the entire process. So recall that our system of linear equations was something like this, right? So we actually don't have to calculate the 2 points simply like that, right? So what we are going to do is we are going to solve this system of linear equations, but now the trouble is that we don't know the value of RF, right? So we are going to keep RF as a letter itself, right? So we'll keep it as it is, and we are going to solve for Z in terms of RF, right? So we will get expressions like this. So Z1 will be equal to C01 plus C1 times RF, right? So some linear combinations of RF will be all Zs, right? So Z2 will be C02 times C12 times RF, and so on and so forth. So all Zs will be in form of something plus something times RF, okay? And what we are going to do is next is that we are going to plug in two different values of RF. For one value of RF, we'll have one set of Z values. The other value of RF will have other set of Z values. And we'll translate those Z values to X values, and then we have our 2 points, right? So that's basically the entire process. Okay, so let me reiterate the process again. So a bit complicated, but not that complicated, right? So again, like these are our inputs, returns, variance, and covariances, right? And solve this. What we are going to do, we are going to solve this entire system of linear equations for Z using Gaussian elimination in form of RF, right? So previously we solved for Z, but for the exact numerical answers. But now we are going to solve for Z which are basically going to be a linear equations in form of RF, right? And so we'll plug in two different RF values to get two sets of Z values, same as the and after that it's going to be the same as the last procedure, right? So we can calculate the set of X values by normalizing those Z values. And so these 2 points, these are basically like 2 points in our efficient frontier, and the rest of the efficient frontier is just any combination of these 2 points. Okay, so that's pretty much it. All right, so now we are going to do something more. So previously short sales were allowed, but we are now going to forbid short sales, and the riskless borrowing and lending is still allowed. Okay, so the line is still there now, but the curves that we had, they are no longer going to all the way to infinity, right? So our job is very simple still, like we just still have to calculate what we did in the very first case, which is we can still maximize our theta with for this expression, right? So we have our RP, we have our RF, because risk-free borrowing and lending is allowed now, and we have our RP sigma p, and so all we have to do is just maximize the theta. So we previously had this constraint, which is sum of xi equal to 1. We still have that, but in that in addition we have one more constraint, which is xi's are all greater or equal to 0, right? So short selling is not allowed, which basically means that xi cannot be negative, right? So short selling, where we basically short sell something even if we don't own them, so where that corresponded to negative xi values, so that is no longer allowed anymore. Okay, so xi's are greater or equal to 0, and this is like slightly harder than the first case, because in the first case we substituted this sum of xi equal to 1, this equation, directly inside this, so that we basically got rid of all the constraints and we simply just maximize theta by using derivations, right? So here we can't do that because we have one more constraint, and this constraint is it cannot be substituted like that in the equation, right? So we'll still always have this constraint. So the good thing about these two constraints is that these two constraints are linear constraints, right? Nice little linear constraints. The objective would have been linear, it would have been amazing, but it is not linear, because RP is still linear, because RP is xi times Ri, Ri's are constants, and so xi, it is linear in x variables. RF is fixed constant, but the sigma p, right? So this standard deviation part, this is it involves squaring of xi's and multiplying two xi's together, and then at the end taking a square root of this entire expression. So all of this is nonlinear, right? So it's basically all of those operations are quadratic operations. So all you have to do is just write these equations in so that there are basically solvers for that, right? So this kind of optimization problems, they're called quadratic programming solvers, right? So all you have to do is just that there are like nice little methods for solving this quadratic programming problems, which I'm not really going to go deep into it, because it's super math heavy. It involves KKT conditions and all those things. So we're not going to go into that, but the idea is that those techniques are known, the algorithms are known how to solve them, and so there are commercial softwares available for that, and you just have to model this entire requirement, right? So you have to model what the objective is, which is maximizing this portion, which has your quadratic terms, and you have to define the constraints, which is sum of xi should be equal to 1 and xi should be equal to greater or equal to 0. Plug in those everything, plug in all of these numbers, and the solver will calculate the optimal values for which the theta is maximized. Okay, and that's precisely what we wanted, right? So once we have that x values, then we have the equation of that line segment, which is precisely what we which is precisely the efficient frontier. All right, so the last case is that nothing is allowed, right? So short selling is not allowed, and riskless borrowing and lending is also not allowed. So we no longer have the line segment also, and all we have is just this is similar to the second case, right, where we didn't have the line segment, but all we have is just one small portion, which is small portion of the curve, which is not really going to infinities, right? So that small portion of the curve, it's very simple, right? So it is basically for any given return, all we are trying to do is minimize the risk, right? So whatever return is given, and if we try to minimize the risk, we go as far as we can go for minimizing the risk, then we'll hit something, a point in our efficient frontier, right? So that's what we'll be trying to do in by trying when we're trying to find the efficient frontier, right? So we are going to minimize the risk. So instead of minimizing the sigma p, we are going to minimize sigma p square, which is like a lot easier expression, right? So this is the expression. So again, like a quadratic programming kind of objective, because there are multiplications of x variables, so not linear in x. And we have our constraints which we had before, sum of xi equal to 1, and all xi's are greater or equal to 0, and we're going to find this x values for a particular return, right? So let's say I want a return of 5%, and so what we are going to do is we are going to find out the point where the return is 5%, but it minimizes our risk. So that point that we find is in our efficient frontier, right? So we find one point like that. We find one more point using again this kind of RP bar, some other return. So basically, like essentially, you have actually solved this entire problem, right? So for any target return, you know your investments in each of the securities, which is going to minimize your risk. So you are essentially, you know how to land in the efficient frontier. Okay, so this is how you can do it, right? So again, like these are quadratic programming problems. Just plug it into the quadratic programming solver and it will give you the answers. Okay, so the last point I actually wanted to stress on a little bit is that we can actually have some additional constraints as well, right? So now that we are in the quadratic programming space, because we landed into this kind of quadratic programming space because the short selling was not allowed. If the short selling was allowed, which was the first and the second case, then we didn't have to go through this quadratic programming kind of stuff, right? So everything was linear before that, and if you imagine the short selling was not allowed, then solving linear equations would be sufficient. But let's say if we landed into this kind of scenario where we are solving quadratic problems, then we can actually incorporate some additional constraints as well, right? So for example, a constraint like this, right? So let's say that you have a target dividend in your mind for your securities in your portfolio. Let's say capital D is what the target dividend that you want to achieve, and let's say each security is giving you di amount of dividend, right? So you can have, along with the other constraint, you can also add one more constraint like this, and you are done, right? So the solver will basically take care of this constraint, and you will achieve a portfolio for which the return is what you want, the risk is minimized, and you are getting the dividend that you want, right? So of course, like if it is possible, right? So if it is not possible, then the solver will cry and then it will say that this is infeasible, and so you'll basically not get anything. So of course, like, but then like you can play along with different values of D and different values of return that you want to get. Okay, so that's one set of constraints. Some more constraints a lot of people are interested in is basically having constraints like this, so that I want to invest at least say 2% in every security that I'm considering, right? So you can basically say something like the xi's are greater or equal to 0.02, right? So this is the same thing as investing at least 2% in every security, right? So I have carefully selected my securities, so I want to invest in all of them. So some people have this kind of requirements, right? So they don't because otherwise, in sometimes what will happen is that in some optimal answers, some of the xi's will be equal to 0, and some people want to diversify a little bit, so they add this kind of constraints, right? So some people also want to, like, what do you say? So there is a saying that, don't put all of your eggs in one basket. So they want to limit their fraction of how much they put in one security, right? So they can have upper bounds on x also, right? So x size, let's say less than equal to 0.5 or 0.3. So this is same as saying, don't put more than 50% of my total investment in just one security, right? So you can have many more constraints like this, and all you have to do is just give it to the solver, right? So the solving algorithm does not change. It's still the quadratic program. And so even when you allow short cells, but if you have this kind of additional constraints, then you can still use this quadratic programming formulation, and that That way you can basically get your answers. Okay, so let's quickly summarize what we have seen in this chapter. So we saw how to calculate efficient frontiers when short selling is allowed and risk-free lending and borrowing is allowed. So this is just simple taking derivatives and solving a bunch of linear equations, and that's it. Right. So it's very easiest case. And second was short selling was allowed, but risk-free lending and borrowing was not allowed. And so this is slightly complicated case where we had to like basically find 2 points and then calculate the rest of the efficient frontier by taking combinations of those 2 points and efficient frontier. The third one we saw was where short selling was not allowed, and this is where things started getting complicated, where we had to use a quadratic programming solver. And same for when short selling was not allowed and risk-free lending and borrowing was also not allowed. We still have to use quadratic programming solver. And using that, we can also incorporate additional constraints like how much dividend we want, how much, and basically, like say for example, more constraints like let's say if you want to invest at least certain portion in certain industry or certain segment of the market, then also all of those additional constraints can be handled when you are using quadratic programming solver. Right, so this chapter was a bit math heavy, of course, and in the next chapters we're going to simplify things a lot. And yeah, so that's what we'll talk about in the upcoming chapters and see different models for simplifying things. Right, so hope you learned something new, and don't forget to subscribe if you haven't already, so that you don't miss an episode when I upload. So see you in the next chapter.